talking about active matter.
Well, okay, thank you to the organizers for this opportunity. What I'm going to talk today is about a very different problem what you have been talking in this meeting. And here are the collaborators. Okay, let me show you what I'm going to talk. What I'm going to talk is about clogging in bottlenecks, right? Clogging is a very common problem that you have suffered when you are in the high roads, in silos, in air grains, also in crowds. And probably you don't know this, but it's also in medicine is a technique that is used to kill cancer, because they put particles, microparticles in the veins to create clogs here in the veins and arteries, and then prevent the fluid arriving to the tumor, and then this is a technique that is used to kill cancer. I want to emphasize the use of this word, clogging, and not the word of jamming. I used to use jamming a long time ago, but I like to differentiate now, because I think this is a rather local problem. Probably the situation here, the properties of the system here are different from the properties of the system there. And because of this, I prefer to use the word clogging, right? Okay, let's start with a very simple problem, apparently. It's a silo, and what you should know about the silo is that, okay, what's the important magnitude is the outlet size, or the outlet size compared with the size of the particle, and which is going to govern most of the things. Okay, and then if you fix this magnitude, and you have an avalanche, if you break the arch that is clogging the structure, what you have is an avalanche, right? You have some grains flowing, and if the outlet size is not much larger than the particle, what you have is a clog. And then you can measure the number of particles in those avalanches, and what you get always is an exponential tail. An exponential tail, this is the size of the avalanche, that can be easily explained if we consider that the particle clogs, well, the particle passes with a probability p, and clogs with a probability 1 minus p, and then the size of the avalanche is this expression, p to the s, multiplied by the probability of clogging. This is quite, well, boring, let's say, because it's an exponential tail. Everything is well defined. The first moment of the distribution is well defined. We can calculate it analytically. And then the mean avalanche size is the parameter that we will use to explore what happens with R, with the outlet size, or the ratio between the outlet size and the particle. And what happens is that this is a semi-log scale. The mean avalanche size seems to divert, but this is, I haven't put here any fitting, because it's still under discussion if there is a real divergence or not. And this is one of the messages I want to bring here today, that it's still not known if there is or not a divergence here, because we arrived to do experiments that the mean avalanche size was 1 day, okay? And still we were far from the apparent critical value of R where should be the divergence. The other thing that I think is related, or somehow related with this, is that when you increase the outlet size, of course the flow rate, the number of particles per second, or the mass per second, increases as well. This is well known since the 60s, because Weberlu proposed an expression for this, but still not any fit here, because still there is some discussions about what are the parameters in the Weberlu expression, which this is a value of k that is not clear for the physical meaning. And well, last year we proposed some modified Weberlu expression to give some sense to the parameters. But the important thing here is that modifying the outlet size, you modify both things, the clogging probability and the flow rate. And the question is if those things are related or not. Typically, engineers have related those things, flow rate and probability of clogging, but it's still not clear. Then when we forward and we play a bit with the silo, and we place in an obstacle. This is somehow related with the work that Mark Medel presented yesterday. What happens here is that, okay, placing an obstacle, you see here the particles. They are trying to form in arches, but the particles can jump there, because, of course, the packing fraction here is low, but also the pressure here is lower. There is a drop in pressure, as Mark showed yesterday. And this behavior is not observed there, right? This is just placing an obstacle just above the outlet. And what happens, the effect of placing this obstacle is quite striking because it prevents clogging. I don't know if you get, okay, this curve is, I don't know if you can see that. Okay, here we have the obstacle, the position of the obstacle, the distance from the bottom of the obstacle to the outlet. And if we look at one of those curves is for a given outlet size, what we find is that if the obstacle, the position of the obstacle is far away, it's 10 particle diameters, for example. These particles are 1 millimeter, 10 particles diameter, 14. The mean avalanche size, the probability of clogging, is the same that if there were not obstacles. When we approach the obstacle to the outlet, what happens is that the mean avalanche size increases, and increases up to 2 orders of magnitude. Okay, we have avalanches. We can have an avalanche of 5 seconds until 500 seconds, just by placing an obstacle. And the same happens with the other outlet sizes, and this is quite striking, but probably it's more striking that, okay, I'm taking this mean avalanche, the maximum avalanche size that can be got with the obstacle position. I plot in this graph that I plotted before, and then I plot the flow rate that I got in these situations, and the flow rate is almost the same. Okay, those 3 points are those 3 ones for the flow rate. Those ones are for the mean avalanche size. With the same flow rate, we get completely different clogging probability, different mean avalanche size. And this is quite important for 2 reasons. First is the fact that the clogging probability does not depend anymore only on R, on the outlet size. That was the star of the silo problem, right? Now there is something else. This is quite interesting. And the other interesting thing is that we can separate flow rate from clogging probability. We keep with the same flow rate, but modifying something, we change the clogging probability. And this is quite interesting because there is not a direct relationship between flow rate and the clogging probability. And then when we were there, well, indeed, the idea of placing the obstacle was taken from crowd dynamics because, well, there is this idea that if you place an obstacle in front of an exit, the evacuation time of a crowd is improved, right? And then we took that idea, we worked with the silo, but then we started to look at the literature of this problem. Probably the most famous paper is this one of Helvin, but there are others. But in all the cases, the experiments are, well, 6 experiments, 6 tests with obstacle, 6 tests without obstacle, with the students. Okay, although they are students, panic is not, you cannot create panic because you can get in troubles. And then we say, well, we have to do something. This will work, it's real, this problem. And then we do experiments with those guys there. We went to a village, a small village in Aragon, and then we find an obstacle there. We put a video surveillance system. There is not electricity there, then we took the battery of the tractor, and we put all the cameras, and we do the experiments, right? The experiments are daily, 1 experiment per day. Daily, the sheep are taken out of the yard by the shipper. The yard is cleaned up. Food is placed inside the yard. Then the door is opened, and of course, all the sheep crowd in front of the door because they want food. The door width is more than twice the sheep width. Well, the sheep width is measured here, right, in the wider region of the sheep. Not that, I'm not talking about aspect ratio, sorry, Thomas. Then we have around, well, the shipper has around 100 sheep, and the experiment, 1 experiment consists in 20 days without obstacle, 20 tests with the obstacle larger than the door. Okay, of course I have to show a movie because, and this is what happens. Okay, now I think, well, no, now I'm not going to talk because you are not going to listen. Okay, why sheep? You may ask yourself now why sheep, and it's not. I mean, it's not an easy question because the only few experiments that have been done with these things are with ants. and the behavior is completely different. Ants are like, well, a guy that works with ants says that they are genetically constructed to be social, to don't panic, and sheep are not. Sheep are like humans. They are, no, it's true. I mean, they crowd and they clog, right? Have you seen clogs, right? Okay, what we do, no, it's time, not serious. Okay, we take a line of pixels there, then we build a spatio-temporal diagram of our ships. The ships here have different strange shapes, but this is just because they pass with different velocities, right? This is a spatio-temporal diagram. And then it's very easy to count sheep here, and then we count the number of, you should listen, I mean, you are just laughing. This is the number of sheep versus the time they have passed, and this is, with obstacle is red, without obstacle is blue. Apparently there is not a huge difference, but if you look carefully, you realize that these horizontal lines mean times where there is not been, horizontal lines, time when there is not been sheep passing through the line, are more likely without obstacle. I'm going to show that. Okay, but before, let me talk about some things. I'm going to show the clogging times, and when I talk about clogging times, it's just the time between one ship and the next one, right? That's the clogging time for me. I'm going to measure all the clogging times. Some of them are not clogging times because just passing time, but I'm going to plot all of them. And then I will come back afterwards to define what is the bus size. When you plot the clogging times, it's quite interesting that what you find is a power law tail. This is the cumulative histogram, and okay, we have more than 5,000 sheep, I think, passing because there were more experiments. And here you have these clogging times. Without obstacle, you get this exponent. With obstacle, we have this exponent. Here, being in an Institute of Mathematics, I have to refer to this paper. That's been very useful for me to do all the fittings, because one of the most important questions here is if it's really or not a power law. And if you go to this paper, I think it's very, very useful paper to do empirical power law, empirical fittings. All the programs, they have put in the web all the programs in MATLAB, C++, etc. It's very interesting. It was a nice discovery. Okay, this happens with and this red line, green line, is with this program as well, you can get the minimum value after which the power law tail, the power law is starting to work. And then this is 0.5 seconds. That is more or less a time associated with the passage of one ship, right? And we use this time when we have a clogging time larger than 0.5 seconds to define the beginning and the end of a burst. This is a burst, right? The size of the burst is, in this case, 17 sheep, because it has a clog of larger than 0.5 seconds before and a clog of larger than 0.5 seconds afterwards. You can change this to 1 second, and more or less you get the same results. Of course, not the mean clock size, but the distribution of the clock size, the distribution of the size of the clocks is exponential. Okay, then things become boring because you can't define the mean. Well, boring, not that you can't define properly the mean, and as in the silo, you can. Okay, and then we say, okay, sheep experiments are very difficult, and we went back to the lab. But the comparison with the silo is not straightforward, because in the silo, particles, granular, dissipate energy. Once you have a clock, the clock lasts forever. And sheep, no. Sheep have some kind of internal energy that are able to break the clocks, right? Then we decided to vibrate the silo. Of course, it's not the same because we are applying energy. It's not the particles that have the energy, but we can apply the energy and control it. And we did the experiment. This is a shaker. This is a silo mounted in the top of the shaker. The silo can vibrate. Everything is automatized with the computer. And then what we do is let the grain flow until an arch is formed and stops the outpouring. We apply a vibration. Well, we will call the amplitude or the gamma. We fix the frequency to avoid okay, exploring many parameters at the same time. We will work just with the amplitude. We have explored several frequencies, but it's not the case now. Then we detect the arch formation and the arch breaking, okay? And then we can take those times, and then we empty the silo, and we repeat the experience thousands of times. That's the controlled experiment. Again, the avalanche sizes there are exponential. You can define the mean avalanche size. The time that it takes the system to clog is well defined. But when you go to the unclogging, the time that it takes to the system once you apply the vibration to break, to get unclogged, you get these distributions. And what happens is, again, you get the power laws, but it's even more interesting. What we get is that for low amplitudes, we get a power law with an exponent 1.6. When we increase, then we increase the amplitude, and the power law, the exponent increases from 1.6 to 2.2. Okay? And this is very interesting because a power law, a decay in a power law with an exponent smaller than 2 has not a well-defined average. You cannot define the average there. The average is diverging. An exponent smaller than 2 is diverging. Higher than 2, you can define the average. The average is well-defined. Okay? And this, okay, then we explore what happens when you increase R, the outlet size, and you get the same behavior. You can go below this exponent 2, and you can go up, increasing R. You can go up from the exponent, and you pass from a distribution that does not converge to a distribution that converges. And if we work with a high layer of grains in the silo and a low layer of grains in the silo, it happens the same. High layer of grains, we have a non-convergent distribution. Low layer of grains, we have a convergent distribution. And this is, for this problem of the ship, or the grains, very, very important. Because this means that if we are in low gamma, low R, or high layer of grains, we cannot define the average flow rate. And this is something that is being used a lot in crowd dynamics. They take one measurement, and then they define the average flow rate. And here, the average flow rate cannot be defined because you have a flow with exponential distribution, which is well defined, and then you have clog with a power law that does not converge. And then the times of clogging diverge, and this means that here the system is clogged, and here the system is not clogged. Here you can define average flow rate. Here you cannot define rigorously the average flow rate. And then this can be used. This strategy can be used to define somehow a clogging transition. Here you are clogged. Here you are not clogged. Here you are clogged, not clogged, etc. Okay, I think this is all I wanted to say. Just exponential and power law, different distributions, the importance of this exponent, and just remind that probably placing the obstacle in the ship, that you recall that it was increasing the exponent, has a similar effect that reducing the layer of grains in the silo is reducing somehow pressure. And now there are a lot of work in progress. This is a numerical guy that is used to work with Helbing, that is applying these pedestrian models to this, and he's finding similar results. And also is Raúl and Ignacio Pago Navarraga are doing the same for colloids. Thank you very much.
No need to be sheepish. Is there any questions?
I have a practical question for the meat industry. They do have clogging. That is a bit of a problem. And so what is your recommendation? To put an obstacle or not?
Where?
In the meat industry, you know, the beef industry or the...
Before or after cutting?
In other words, would you recommend that they place an obstacle or not? I didn't quite see at the end what your recommendation would be for them.
I will recommend to place it, but you have to be careful where you place it. I mean,
right.
You have to be careful because, okay, this is.
We'll get a bigger door.
Okay, if you go too close to the door, you may be in trouble.
Yeah, sure. I wasn't sure from when I looked at the next few diagrams whether you had concluded this was useful or not. Yeah, here, this one.
Yeah, here, the obstacle, the clogging times are reduced.
Okay, I got it.
Probably you have similar clogging events. Not really, because you have less. But what happens is that the clogging times are reduced. Important.
But this was a very simple question. On the picture with the grains, we had the impression that the obstacle was close to the side wall. Well, is that true? And could you show us again?
The movie.
That one, yes.
This side, this is, I mean...
this is just a cut view out of a wider...
This is very, I mean, yeah, this is something that took us a lot of time to put exactly the obstacle in the middle of the orifice.
Yeah.
And of course,
what's on the side of the obstacle? Is it?
Here?
Yeah.
No, here, the silo is...
Oh, okay, all right. Okay.
The silo is, I mean...
Okay.
It's something like 50 or 100 particles width. I mean,
Okay, that was a simple question.
the walls are far away.
Walls are far away.
Yeah. Just a zoom of the movie there.
Yeah, what does it mean that the average doesn't exist? Is it that if you...
Yeah, if you do the integral, it doesn't.
But is there a drop-off after that, or is the event just having some fractal damage?
That means that one time you will have a clock that will last forever.
So it depends on the waiting time.
So, in some sense.
Yeah, and it's what happens with the power law decays. I mean, if the exponent is between 2 and 3, you have noticed the standard deviation. The second moment is not convergent. You cannot calculate this.
So normally, when you have power laws, you expect another fast decay after that. And then you converge it after some time scale.
In this case, I mean, well, all what can I say is that here in the silo, we have the opposite problem. We had this here because there are some arches that last for, well, at least for half an hour. We have the opposite problem. It seems that there are some arches that are very resistant, that some structures that are very, very strong. Which is good for us. I mean, for us, this is clogged, then, well, we would know it.
Okay, so Ika has given us lots of room in Ancon, everyone.